Okay, welcome back. So, we're going to go through a couple of the projects in the class code repository. This is pre any kind of refactoring or changing, so this should line up exactly with Alberto's code. But for the most part, you'll find that the content will stay largely the same, if not exactly the same. So to start, in the last coding example, we went through this project, which this is sort of the final version of what we built before. If you can recall, we created our own window, and we did everything kind of by hand, and all this work was done to make this work well. Great. And if we run this, and we debug it, start the new instance, you might recall this green triangle, and when we want to quit, we get out of there. It's out of there. Okay, so now, what if we wanted to do it a little bit faster and use something like SFML to create the window? So let's open that up. This is a project that's already in live. I'm not going to be coding everything from scratch. That takes way too long. But if you have specific questions and ideas for things, please feel free to give me feedback on the Discord and in general. And so let's quickly run this and just see what that looks like. So start new instance. And here we go. It creates the OpenGL window and draws a triangle to it, just like we did before. Note we have a couple of things here in the console that we didn't have before. Warning, the created OpenGL context does not fully meet the settings that were requested. So why that be? We'll look through the code and figure it out. And we've requested version 1.1, 32 depth bits, stencil bits, and all this stuff. It looks like a lot of work that somebody did to make all this come up correctly. Work we didn't have to do. So to start, you'll notice that we took that the shader code and we've moved it up here. And so now instead of it being inside, we can actually kind of edit it up here. But for the most part, it hasn't changed. It's mostly the same code as we saw before. So let's kind of go through this a little bit and check out what's changed. One thing you'll notice, and this is a pretty huge change, to initialize the window, it's really just this line of code, right? So like just for comparison, let's open up the previous example. In this case, we started here, so line 54, and it wasn't up until here that we set the GL clear color like we did, here. There's a couple other things here. Obviously, we implemented blue. We had to do that here a little bit. But really, we kind of avoided all of this with the exception of maybe that, right? That's a lot of code. That's like nearly 150 lines of code. So a lot of stuff, and a lot of also code we don't really want to write. It's not like this really needs to be done by us. And so SFML does that by way of this really convenient function or object called window. You pass to the window your video mode. If we take a look at what video mode means, we got the width and the height, and by default we have bits per pixel, 32-bit depth, which is a nice little feature. We're using default, and so it's going to give us an 800 by 600 width sized window. It's going to give us, this is the name, the title. It's going to have the default style. I'm sure we have other styles, not many, I guess. And also the context settings, which is going to give us the depth buffer most likely. So really, really convenient. But apart from this, and apart from some of these functions here, which I'll talk about in a minute, the rest of the code is largely the same. We go through, we create the vertex shader and the fragment shader, we compile it, we check if there's any errors, we set up the buffer, pass it into the GPU, and render it, right, with this. in this while loop. There's a bit of a change we made here to the poll event. So instead of doing and checking and peeking the message, we're polling for an event. So this is a bit of a change in the way that SFML handles events, which is a little bit nicer, right? We don't have to have a Windows process function. We don't have to handle things at that level. We simply are polling for any events that the SFML framework is giving to us and handling it, right? In fact, we could very easily switch this up to doing something like this. Switch event type, and then case and then finally defaults. Do nothing. And this should still work, which is cool. Oh, made the mistake of building the thing. I should instead set this as our startup project and build it. We may get an error, no matching token found, because I am a jerk and I didn't do this right. Cool. So now this should actually work. And if we run it, same jazz. Notice if we hit any key, it'll kill it, which is cool. Another way to do this too is if we can check if the event key is equal to 27. What? Key events. We want a key event. Key.code is equal to 27. Then running. So now it will only exit if we hit escape. So nothing but escape. Apparently that's not correct. Let's just really quickly see. If I hit escape, what key do we get? The key code is the event type key escape is 36. Why is it 36? No one knows. You know what? You spend all of your time trying to figure out why code does what it does. You won't write in it. So sometimes it's better if you just deal with it. Blah, 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 escape. It's working now. Great. So, as you can see, for the most part, SFML has replaced a significant portion of our code. Let me talk a little bit about this, right? So we initialize glue here. This is important. If we don't do that, then a lot of the things that we are using here won't be available to us. So this is enabling a certain set of flags in the OpenGL state machine. Specifically, we're enabling GL blend, or the alpha blending function. If you turn this off, then alpha blending does not work, and you can't put items on top of each other that have different alpha values. And if you want to do that, then that's really for transparency, it's for special effects, it's whatever. You do need to define a blend function. And so the blend function is you're using the alpha as the source of the blending function, and then this is the type of function, which is 1 minus the source alpha. And there's different blending functions. In fact, if you really want to know what they mean, what you want to do is you want to Google them, and this will pop up. Go to the documentation, and you can kind of see the values and what these things mean, right? If it's a 0, it's a 1, it's pretty simple, right? 1 minus source color, and so you have this minus the R aspect and so on. There's a better way. There's usually a better. Here we go. That's what you want to see, right? So we're using the 1 minus source alpha. So 1 minus source alpha. So we have the 1, meaning the color that is the source, the destination, and then we have the alpha divided by the Ka, where the Ka, what's the Ka stand for? Well, usually it's just 1, I think. I think that's the maximum value. It's kind of, usually this stuff is done in floating point, and so either way, this would be the alpha of the source. So hopefully that makes sense. We'll talk about blending functions if we dive into transparency. It's not something you really need to worry about too much, but generally speaking, 1 minus source alpha or 1 minus dest alpha will just kind of figure out which one is on top. And so this is usually the function that you use when you're doing this type of thing. Depth testing is something you usually is default enabled, but depth testing allows you, like say I'm rendering one triangle and another triangle, and one is at a closer z value than the other, then how do you know which one to actually present, which pixel is the one that should be rendered? If you're dealing with alpha blending, like one is kind of transparent, that calculation is a little bit more complicated. But if it's just an opaque triangle that's in front of another opaque triangle, then for the most part, you don't really have to worry so much about anything except for testing the depth test. So this fragment will have a depth associated with that fragment. When you render it, we'll only plot that to the screen if, and only if, that point is closer to the camera than what's currently there. So if I render this triangle and now I'm rendering another triangle, I'm not actually going to render the stuff behind here because, or at least it's not going to show up to screen because there's no point. And so the type of depth testing, so you can imagine when there's two things really, really close to each other, how do you do the testing? And so this allows you to manipulate that. So either it's less depth or equal, meaning if I render something that's at the equal depth, it's actually going to render that after all. But you do have other options, right? You can also do greater than, you can do not equal, you can do less, you can really play around with this stuff, which is important for, in particular, effects like shadow casting and things like that in the future. And then finally, this is a very nice feature because it will significantly reduce the number of triangles you have to render. So if you're looking at a triangle from behind, it will not render the triangle. And it's really simple. It's just a dot product of the direction of the normal to the way you're rendering the triangle. So if you're rendering a triangle, you know the vertices and the orientation, and then you can kind of figure out the normal, and this is all done in hardware, so you can kind of figure out if you're pointing away or towards. This is not done with the normal you're passing to the GPU, by the way, and that's a really important point to make. It's only going to be dealing with the ordering of the vertices. So this is something to really pay attention to. I'm noticing there's like a bunch of light on me from this sun situation over here. I'm gonna just jump really quickly and lower the shades. kind of sunny. But no way to fix it. Oh well. Better than nothing, I guess. Anyways, actually, nice, perfect. All right, that's a little bit better. Sorry about that interlude, and we're back. Yeah. So for the most part, that's really it. You'll notice these convenience functions, like I can get the size and the position of the window, and that's a nice thing to do that with straight Windows code is not the funnest thing to do in the world. So a lot of benefits in using SSML. As you can see, it's really simplified our code. What was before like a 300-line file is now half that size, which is pretty nice. And the one thing you have to do, and I think this covers the swap buffers and all of that, is make sure you call window.display, which will end the current frame, present, and swap the buffer. So you do lose a little bit of control, right? If you wanted to do something a little bit more hands-on and deep, you wouldn't be able to do it here, but for the most part, this handles most of what you need, and it's quite powerful. So yeah, fun. Let's just run it one more time just to check out that sweet, sweet triangle. Nice. All right, let's move on to this next project, which starts to add more object-oriented principles and patterns into our code, which is something that we should always try to do. So let's quickly make sure it's built, it's up to date, and let's run it. And actually, let's open up the main. Its main in its code. Cool. So you can already see it's quite simple. The code is significantly simpler than before. So let's run it and see what happens. It looks about the same as before, except the triangle is yellow and the background is blue. So if we exit out, what is going on, and how is this little bit of code allowing us to run all of that we had prior? Well, let's first take a look at the main.h. It might give us a bit of a hint, and you can see it's including this file called appclass.h, and in our main function we're actually creating that class, and then we're calling this function called run. So let's first take a look at app class and what does it have in it. We can already see there's a fair bit of stuff in here, and we can see a lot of structure. And so we're using the SSML window. We've created a window variable here, great. And then we've also have a shader program ID and the VAO, VBO, and whether or not it's running. And you can see some of these functions down here. So A, we have the constructor, the destructor, this run function. We also have a copy assignment, so it doesn't let the object copy because it's private. And we also have a copy constructor that's private, so it doesn't let the object copy, which is nice to have. We have an initialize function, we have an initialize window, in it OpenGL, and it shaders, and it variables, blah, blah, blah. All this stuff, let's go through what that all looks like. So let's first start off with the constructor, because that seems like the best place to start, like what's going on in here. Nothing. And actually, you'll find that in object-oriented programming, usually the constructor does little to literally nothing. Generally speaking, in good object-oriented design, you really want to have your objects constructed, memory allocated in one place, and then initialized and set up in another, because initialization often can fail. As we saw previously, again, the shaders are out here, just to make it a little bit easier to read. And you can see that we're doing a yellow triangle because it's a combination of red and green. And so the run is what we're calling in main. So we're just calling it one time. So run is sort of the entry point. It's almost like the main function of this. We're setting the background color down here to a bunch of stuff. But first, we're initializing the system with everything that we need. So let's take a look at the init function before we can see down here in the run. We're just now running the main loop. And with the slight difference that we now have this function down here, display, which belongs to our object, instead of previously where it was swap buffers and all of that. So let's take a look at the init function, which is right down here. And init further kind of breaks it down into 4 different initialization stages, much like we had when we created our first OpenGL example. We kind of created these regions. This will also sort of create regions, but in the form of functions, which are a little bit easier to understand and digest. So first, let's take a look at init window, which takes a name, and the name is really just the string name, and it just calls that function. That it just creates that window like we saw in the previous SFML example, with a size of 800, with the window name that we're passing in as a variable, default settings, and the 32-bit depth. Setting the vertical sync enabled, and there you go. And that's all init window really does. Then OpenGL, the initialization of OpenGL, the next thing that happens, just like before, we set up glue, we enable blending and set up the proper alpha blending function. We enable depth testing and then set the depth testing function, and then we also add calling the face functionality for OpenGL. So again, it's very similar to our previous code. In fact, it's the same, except for the fact that it's sort of split up into these functions that are discrete units. Next, we have our init shaders function, which again, just we load up the vertex. We set up the vertex shader on the GPU. We load up that code. We compile it. Same thing for the fragment shader. Then we create the program. We link the program, and then we test for any problems. And then we delete the vertex and fragment shader. And then finally, we init the variables. This is the geometry stage. Let's take a look at that. We can see here we're setting up a triangle, just like before. We're setting up the VAO, the VBO, we're passing the data into the VBO, and then we are binding the position buffer location in the shader that we defined up here to that VBO and to that VAO, I should say. And yeah, that's really it. That's all the initialization does. As we pop out of init, we set the clear color to this color, which is that nice blue we saw before. And then again, we create a loop that is will exit if running is ever equal to false. And then we will pull this event, which is we're going to check SSML for any Windows events that may occur. And then we're, just like before, if somebody hits the keyboard event and we want to process the keyboard, so we've kind of popped this out into its own function. We're also doing this call, which we did in the previous one, but I didn't cover it. GL viewport will simply, if you're resizing a window, will resize the viewport of your OpenGL context, which is not something that happens automatically, so you do need to handle that. And then, so yeah. So first let's look at display. Well, let's look at process keyboard actually, because it's probably going to be quite quick. You can see it's a very short function. If we've hit is key pressed escape, then we quit. So this is a slightly more eloquent way than I did before of quitting on escape. And then finally, display is called every one of these loops. And so let's take a look at that. And in display, it's going to clear out the buffer bit as we were doing previously. It's going to draw the triangles. Note that the VAO is already bound and the VBO is already bound, and so you don't have to, for the time being, change those. And then again, we're going to call the display function from the window, just like we were doing in the SSML example. As you can see down here, it was calling the display. The reason we have to use the arrow is window is no longer a object, like a static object. It was dynamically allocated. If you remember, this is a pointer, and so when we were initializing, when we initialized the window, we created a new window. So instead of, and previously in this function, in the SFML example, we didn't create a new, we didn't dynamically allocate that. We simply created, a static variable. It's going to be sitting on your stack there. But here, this is memory that we've allocated. You can do it either way. There's no specific reason why you want to do it dynamically in the context of something like this, except for the situation where you imagine you are changing it. But this is also kind of better design, more mobile design, more portable, generally speaking. So you also have really direct control on when that memory is allocated and deallocated. As you can kind of see in the destructor that we have a function called release, and that's where we're going to go to deallocate everything, including the shader and the VBO and the VAO. And so here we also have to add, well, if window, right, is not equal to the null pointer, then let's delete it and then set it to null pointer. This is kind of an extraneous thing you might think, but it's a really good habit to get into. It's a pretty unsafe thing to do, to leave what's called a hanging pointer after you've deleted it. So highly recommend just setting it and forgetting it, because then you can't really worry about something like that kind of blowing up in your face in the future. So yeah, cool stuff. You can see how this class makes our main function significantly simpler, and also would allow us to take this app class and subclass it or inherit from it and create a very reusable type of architecture in the future. So cool. Hopefully you can kind of see the value of all of this encapsulation immediately. So finally, let's talk a little bit about this next example. Let's start it up and run it. So let's build it before we take a look at anything. And let's run it. So debug, start new instance. Again, it looks kind of the same. So what's the difference in this particular one? Like, let's run this one and see how different. We're not going to cover this one, but you can see some cool stuff's already happening there. So why is this one, the shader compiler project, sufficiently interesting to be its own project? Well, let's take a quick look at the code. Main, we sort of see a similar pattern as we did before. Notice when I said earlier, like that pattern of deleting stuff, you should always safe delete, or should always handle the hanging pointer. So in the main.h, we've defined this macro that will let you safe delete it, which just sort of does that little bit that we did kind of automatically, which is a nice thing to have, and kind of scopes it correctly and safely, so you don't have to worry about it in the future. But you can use either or, the if delete, if null pointer, whatever. It's really up to you. So one thing's the same. We have this app that's calling run. So let's quickly take a look at the app class and see if anything's changed here. So one thing we'll notice is we put the window name into the app class. That's a nice feature to have, because maybe you want to access that name other places. But for the most part, everything's the same. So what is different? Well, let's take a quick look at the code. So running through it, we see the only big difference that we've made here is the constructor now takes this value as a window name. So that gets then set with this, what's called the initializer list. And this is just a nomenclature in C++ to automatically set a variable, a member variable, to a parameter that is passed into the constructor. It's just a kind of convenience function, and so on. And so we've got the copy constructor, and we've got the copy operator, which is set to private, as you remember, so that we can't actually access those in the future. So we can't copy this very easily. And the destructor calls releases before. Run, initializes, clears the color, all this stuff is the same. In fact, everything is the same, except for one thing. You'll notice that init shaders is significantly shorter. And that's really nice, right? If you remember before, the code to initialize the shader was probably the ugliest code in this, right? We have to load it and the stuff, and you have to remember all this crap, and then you delete it, and you have to check for errors. So this is quite the most complicated function in here. Here, it's just a one-liner. And you'll notice that now in app class, we're also including this shader compiler .h. So let's take a look at that, because that's clearly where load shaders is being called from. So let's open up shader compiler.h, and really it's just a function. So there's no objects here. It's just this one function call. You could wrap it in a function in an object if you wanted, but it's up to you. And it takes two variables: this vertex file path and the fragment file path. And what these are basically going to take a file and load it from disk. And so you'll notice that. Another thing that's missing here from our previous example is the shaders aren't up here anymore. They're somewhere else. Who knows where? All right, let's find out where. So it calls this function, load shaders, and it provides shaders dash minimal.vs. So I want to kind of point out, this is something I ran into in my own OpenGL coding example previously. If I right-click and I look at the properties, and I look at one of the post-build steps, you'll notice that it's doing a couple of things. It's copying the shaders of the simplex, include simplex shaders, to the binary shaders. And what does that mean? So the solution directory, the output directory of this project, right, if we take a look here, the output directory is going to be z-delete. General. Okay. Never mind. This is not super helpful. Okay, when I build this, let me clean it first. I'm going to build it. And you'll notice that it builds. It's going to output the code first to z-delete. And then it's going to copy all the shaders as well. So let's kind of find that. Let's find that. So let's go to my development folder, and we are in the C04 shader compiler project. So there you are. But it's actually copying it to this z-delete folder and the C04 shader compiler in debug. And you'll notice that there's no actual code in here. The exact executable ends up instead in the binary folder. As you can see here, the C04 is right there. And you'll also notice that shaders are in here. And that's because it's copying it from that include simplex shaders. The actual copy, I'm not entirely sure where it's happening, but I'm assuming it's somewhere. And I guess you're just going to have to take my word on that. Well, I'll find it. This is a clever little complex thing that that Alberto must have done. So if you really have questions about how it's ending up in the binary folder, I'm happy to dig deeper, but it's probably out of the scope of this conversation. What's important though is you'll notice that this shaders code is here. This is actually being taken out of the include simplex shaders. So you'll notice that all of these files are here and being copied to the final binary location. So when I call shaders minimal vs, it's actually calling this particular one, which we can take a look at with Notepad. And it's just like our previous code. It's just GL position equals the position buffer with the 1 appended, and then the minimal fragment shader similarly is the same, except instead of yellow or red, it's green. So if we change this, for example, to blue, we run this, right, it'll stay green. Why did it stay green? Well, you'll notice that I didn't have to rebuild anything. So I do have to hit rebuild for the code to get propagated because it's being copied. And so now if I run it, it should be blue. So it's an important thing to note, right? If you're making changes to your shader in this code, you have to keep in mind where your shader is being loaded from. And so while if I run this now, and it's going to be blue, and if I want to make a change here to make it a different color, you'll notice that it's not going to rebuild. It doesn't know that that file has been changed. So I have two options. I either have to rebuild, or alternatively, you can also go into the binary and change that here, right? But what you need to make sure that you understand is that if you do that, right, the next time you rebuild, say this goes back to red, the next time you rebuild, it will clobber that change. So you don't want to do anything valuable, but if you're just messing around with particular variables, it's probably an okay thing to do. So you can kind of see by this point, by C04, we've got an app class that is encapsulating and containing all of the functionality from creating a window, initializing OpenGL, even loading a little bit of geometry, and even loading shaders, which gives us a really nice framework to start to build on and to start to do more interesting things. So yeah, that's covering C2 through C4 in the code repository. And yeah, hopefully this has been helpful for you guys, but please do give me feedback on how things are looking for you, if you like the lectures, if you want me to go deeper on stuff, or if you want me to breeze through things faster. Would love your feedback. This is my first time teaching any class, let alone a class online. So hopefully this is the end of the lectures for this week, and I'll see you next week. Bye bye.